Hey everyone, today we're going to break down a super powerful shortcut in statistics that helps make sense of, well, pretty much everything around you. It's called the empirical rule, and you'll be amazed at how three simple numbers can give you so much information. Let's jump right in.
I know, it sounds a little too good to be true, right? How in the world can just three numbers explain everything from exam scores to the heights of trees? Well, that's exactly what we're about to find out. Let's start with the first magic number. 68%. Okay, just lock that number in your brain for a second. It represents the most common, the most average, the most typical chunk of anything, really. To be a little more specific, about 68% of all your data is going to be found within just one step, or what a statistician would call a standard deviation from the average. This is basically the heartland of your dataset.
Okay, now let's zoom out a little bit. The second number is 95%. So now we're starting to include a much bigger piece of the pie.
That's right. A huge 95% of all your data points are going to fall within two of those steps or two standard deviations from the average. This captures almost everything you'd expect to see.
And for our last number, get this, 99.7%. This is about as close to all of it as you can get in statistics.
Yep, within just 3 steps from the average, you have found virtually every piece of data. And there it is. Put them all together and you get the 68, 95, 99.7 rule. But, to really get a feel for this, we need to see what it looks like.
And that brings us to the visual foundation for this entire idea. The one, the only, the famous bell curve. You might also hear it called a normal distribution.
Just look at that shape. A normal distribution happens all the time in the real world. It's when most of your data points bunch up right around the average, in the middle, and then you see fewer and fewer of them as you get further away, creating that perfect classic bell shape.
Now, the secret sauce here is that it's perfectly symmetrical. The average, or the mean, slices the entire dataset right down the middle. So you have exactly 50% of the data on the left side and 50% on the right. They're perfect mirror images of each other. That symmetry is what makes this whole rule work.
So, let's bring back our first number, 68%. Where does it fit on our beautiful bell curve? It's right there in the middle, the big chunky part of the bell. It covers one standard deviation on either side of the average. This is where you're going to find most of your typical everyday results.
All right, on to our next number, 95%. As you can see, we're just expanding outward from that central block.
And what this shows us is that if you take two of those steps away from the mean in both directions, you've now captured 95% of every possible outcome. We're getting almost all of it now. And finally, let's bring home that all-inclusive 99.7%.
Once you go out 3 standard deviations from the center, you've pretty much captured all the data you could ever reasonably expect to see. There's only a teeny tiny fraction left over beyond this point.
Okay, so that's the theory. It's neat, it's clean, but what does it actually do? Let's see how this plays out with a real-world example, something you might find out in the garden.
So let's imagine we're in a garden, and the height of all the plants follows a nice, normal bell curve. We know the average, or mean height, is 47.4 inches, and each step, or standard deviation, is 2.4 inches. So here's our puzzle. What percentage of all the plants in this garden are shorter than 54.6 inches?
We have everything we need to know. It's time to put the 68, 95, 99.7 rule to work and solve this thing.
All right, first up, we know our target height is 54.6 inches. The next question is, how many standard deviations away from the average is that? Well, let's do the math. We started our average, 47.4. If we add 3 of our standard deviations, so 3 times 2.4 inches, we land exactly on 54.6. So we know our target height is precisely 3 standard deviations above the average.
And because our target is sitting right at that +3 standard deviation line, we know that almost every single plant in this garden is going to be shorter than that. Only that tiny little sliver of data we talked about earlier exists beyond this point.
And that brings us to our answer. About 99.85% of the plants are shorter than 54.6 inches. Wait, how did we get that exact number? Well, remember, the curve is a mirror image. The 99.7% rule covers the area between -3 and +3 deviations. That leaves a tiny 0.3% left over for the two extreme tails combined. So the area in just the single tail above our target is half of that, or 0.15%. That means everybody else, 100% minus that tiny 0.15% is shorter.
You know, solving that garden problem perfectly tees up our final big idea. What do we call that data that lives way out there on the absolute fringes? Well, those are called outliers.
An outlier is really any data point that falls outside of those 3 standard deviations from the average. They are the exceptions to the rule. They're the tallest plants in the garden, the absolute highest test scores. They are the rare, the strange, the unexpected events.
And really, this is the big picture. The empirical rule gives us this incredibly powerful way to separate the ordinary from the extraordinary. Most of life, about 99.7% of it, falls into a pretty predictable pattern. But it's in that other tiny 0.3% where you find the truly exceptional stuff, the outliers.
So remember this, the 68, 95, 99.7 rule doesn't just describe a bunch of numbers. It gives you a way to understand the world, to see patterns, and to spot when something is truly unusual. It helps you find the signal in all the noise. So the question I have for you is this. Now that you know how to spot the expected, where in your life could you start looking for the unexpected?